All right, so we'll get started with reminders. So homework's due tomorrow, okay, um, by midnight, and then exam is still on Monday, okay, because we actually have finished all the content to be covered for both exam and homework 3 before Monday. So those two schedules are not changed, okay. Um, Wednesday lab attendees, you guys will be in faculty 108. All right, and then it's the one that is across the hall to the 105, the larger room, if you don't know where it is, okay. Um, but Friday's lab attendees will be here in this room. For in-seat, today's classroom in disinfection is assigned to Josh and Olivia, okay. All right, so starting from today, we'll be checking on new topic here on electricities, and then that should be the most part for exam number 2, okay? And then for the next 3 homework assignments. But let's get started here. So in winter, okay, so this is a perfect time that you actually have electrostatic charges create probably like on your body. So if you sometimes if you touch the doorknob, you feel like electric shock, and that's because you have electrostatic charges on you built up between your body and the clothes, okay. And then if you get a chance to slide down on of this plastic slides, you will see you actually pick up a lot of charges in that process, okay. It was also demonstrated like a couple hundred years ago by Benjamin Franklin that lightning was related to static electricity. Okay, so when lightning happens, there's electricity generated. So it was already demonstrated it's very dangerous. So do not try. Okay. All right. So basically, if you have one object that is being rubbing with another object, then there's charge transfer or charge will be created. Okay, so then you can pick up small object if the object is being charged. Okay, so you probably have seen this somewhere else, or maybe you have seen this in your high school science class on this. Basically, there are 2 types of charges that can be generated: positive charge or negative charge. Okay, the name was kind of arbitrary assigned. Okay, so it was first discovered and then assigned to the name. So if you would have discovered charge, you can name the way you want it. Okay, so it was arbitrary, but so there are just 2 types of them. Okay, so if you have same charges, then they will repel each other. Okay, so if you've got both negative charge, they will repel each other. Or if you have positive charge, they will repel each other. Okay, but if you have opposite charges, then they will attract each other. Okay. All right. So fundamentally, it's because for materials, they are made of atoms, and then for an atom, they are positive charges at the nuclear side, and then negative charges for the electrons orbiting around it. Okay, so this is a simple model of an atom, but in reality, an atom looks something like this. Okay, you don't see like individual electrons. Actually, you will see like electron cloud kind of distribution. All right, you will have probability of flying electrons at any given moment at any given location like that. Okay. So when you are having one material that is rubbing against another one, then you kind of lose electrons from one object to another object. So it depends on the tendency for the material to lose electron. Okay. So if you have material has tendency to lose an electron, then it will be positive charge, because for the charge of electron, it's assigned as a negative one. And then for the material that has tendency to gain electron, then it will be negatively charged. Okay, so if you are looking for like pick any 2 materials from the list, you will see like which one will be positive charged, which one will be negative charged, depending on their tendency of losing electrons. Okay, or tendency of being charged either positive or negative. Okay. So if an object is not charged, either positive or negative, then it's called electronically neutral. Okay. Now, the sum of the charges should be neutral, should be equal to constant if you are rubbing one material against another material, because one will gain, say, two positive, then the other would lose two negative. Okay, so on the other will gain two negative, so the total will be add up to be the same. Okay, so charges should be conserved. Conserved. You do not create extra charge. Okay, just one being transferred to the other. Okay. And because when objects are charged, they are either gaining or losing an electron. So then charge is actually quantified. It's not continuous. Okay, so the increment of charge is the charge of electron carries, which is equal to this small number, 1.60 times 10 to the negative 19. So this is one of the fundamental numbers. You might want to just memorize that. Yeah. So for charge of electron is 1.60 times 10 to the negative 19 coulombs. Okay. So SI unit for charge is coulombs. Okay. So use capital C for the symbol. All right. 1 coulomb of charge is equivalent to the charge of this amount of electrons, 6.25 times 10 to the 18 electrons. Okay. For the mass of an electron is 9.11 times 10 to the negative 31 kilogram. Okay, so you guys probably would use this constant number quite a few times. So if you want to look it up, you can look it up here. Okay, 9.11 times 10 to the negative 31 kilogram for a mass of electron. For a proton, it's about it's actually about like 1800 times our electron. So this is the mass of the proton. So 1.673 times 10 to the negative 27 kilogram. A neutron is about the same mass for a proton. Okay, they're about the same. It's 1.675 times 10 to the minus 27. Okay, little bit slightly larger than a proton, but about the same. All right, so let's take a look on the first example of this chapter here. It says if you have a system of 1525 particles, each of which is either an electron or a proton, has a net charge of minus 5.456 times 10 to the minus 17 coulombs. How many electrons are in the system? And what's the mass of this system? You can use the fundamental numbers from the slides just before this one. Okay, so you will need the charge of a electron. You'll need the mass of the electron and mass of the proton. Okay. So you can write this in this way. So you can say number of electron as n sub e. Okay. You can say number of proton is n sub p. All right. It says you have a system of these two particles. So you add them up to be 1525. Okay. So that's what you can write. And then the system has a net charge of minus 5.456 times 10 to the negative 17. So an electron carries the charge for electron, you can say E is equal to minus 1.60 times 10 to the negative 19 coulombs. Okay. For a proton, so let me just put E sub P. Is positive. Okay, so electron is negative, a proton is positive, just the same amount of it. Okay. You probably also need them. So for A, I think those numbers are efficient. For B, you probably need the mass of the electron, 9.11 times 10 to the negative 31 kilogram. And then for mass of proton is equal to 1.673 times 10 to the minus 27 kilograms. Okay. All right, so let's take a look here. So it says there are 1525 particles. Okay, so that's the first equation you can write. Okay, It also tells you the total charge of the system is negative 5.456 times 10 to the negative 17. All right, so then you can say, so that's number of electrons n sub e times the charge, okay, which is this guy for electron, negative of 1.60 times 10 to the negative 19 coulombs, right? Now, you also want to consider the charge from the proton because proton also carries the charge, okay? It's the exactly same amount but positive of an electron. So N of P times 1.60 times 10 to the negative 19 coulombs, okay? That goes to the total charge of the system minus 5.456 times 10 to the negative 17 coulombs, okay? So this is your second equation. All right, you have two equations with two unknowns. Then you can solve for the number of the electrons and then also the number of protons here, okay? What we are going to do first is going to, because this is 1.6 here, this is also 1.6 here. So I'm going to divide both sides by 1.6 times 10 to the negative 19, okay? Coulombs. So that get rid of that and then negative, that just that number, but the negative sign should still remain, okay? So then the second equation will become minus, so that's minus sign still here, okay? Minus of Ne plus MP equals to minus 341, all right? So then I'm going to use this equation and that equation to solve for, so Ne here plus MP equals to 1525. I'm going to use these two equation then, all right? So you can do substitution or you can do the other way around. So you can do like, you can add the two up or maybe doing like equation. So then I'm going to call this like equation 3 here. This is still equation 1, okay? Just copy equation 1 down here. So I'm going to just do equation 1 minus equation 3. So that means I'm going to do the left side of equation minus the left side equation 3, okay? Left side equation 1 minus left side equation 3. That should equal to the right hand side equation 1 minus right hand side equation 3, okay? So then this is Ne plus Np minus negative of Ne plus Np. That should equal to 1525 minus 341, okay? So if you do that, you'll get rid of NP because NP minus NP, but this negative negative becomes positive. So then you'll have twice of NE here, all right? That equals to these two add up, okay? So these two add up give you 61866, all right? So then NE is equal to this divided by 2, which would be 933, okay? So that's your amount of the electrons, okay? That's what you needed for part A. Now at the same time, you can calculate what's the number of protons. So the number of proton will be just equal to, based on equation 1, that should be 1525 minus 933, okay? That will be 592 for the proton, okay? So part A down there. For part B, then you're looking for the total mass of the system, which you will, total mass should be from the mass of the electron plus the mass of the proton, okay? You have Ne number of electrons times the mass of electron plus number of protons times the mass of each proton, okay? So that would be 933 times 9.11 times 10 to the negative 31 kilograms plus 592 times 1.673 times 10 to the minus 27 kilograms, okay? So the total mass would be 9.91 times 10 to the minus 24 in kilograms. Okay. All right. And so now we guys got 341 as the first part. So I think you just did the here total of charge divided by the charge of each electron. Okay, but you actually have a collection of both electrons and protons, so you cannot just divide the total charge by the charge of electron. Okay. All right. Any questions you guys might have on this one? Okay, so if you are clear, we'll move on. So the fact that the charged particles can pick up light objects is because for some materials, they can be polarized. So that means for the atom inside the material, so you can imagine this is a large material over here. It's made of each individual atoms or molecules. Okay, so if you have a charged particle approaching this tiny object or small like object, but this is like zoom in to see what happens inside the small object. Okay, so here you will see for each atoms or molecules, because each atom will have positive and negative charge inside it. So they can rearrange the orientation. So you will have negative charges from the electrons to be more on this side, which is closer to the charged particle here, or positive charge in this case. Okay? Because opposite charges, they attract each other. Same charges, they repel each other. Okay, so the same charge will be on this side, the negative charge will be on this side, so that's approaching closer to the object here. So as a result, there's attraction between the charged particle and a neutral particle. Okay, so that's why that would happen. All right. So for materials, um, they are categorized into two types. Okay, one is called conductor, one is called insulator. Okay, so for a conductor, that is a material that it has electrons are free to move throughout the body. So that means there are electrons free to move inside the body of a conductor. Those electrons are called conduction electrons. Okay, and most materials are conductors. Okay, so that means most metals, they have electrons that are free to move throughout their body. On the other hand, as insulator is a material that those electrons are restricted to move from atom to atom. So then they are not conductive in that sense, okay, because they don't have a charge carrier to go from atom to atom. Non-metals are most likely insulators. Okay. Now there's a third type of materials that is in between. It's called semiconductor. So that's a material can be either under certain condition it's a conductor, but on other conditions it will be an insulator. Okay. So those are type of particular material. Okay. We actually use them a lot these days. You can charge a particle by contact, so you can rub against each other, or you can like just bring a charged particle into a neutral one. All right, just in this case. So if you bring a charged rod in contact with this neutral apparatus over here, so then you will see like the charge will be this redistribution between the device and the rod over here. So basically, when there's charge redistribution, that means electrons are moving from one side to another side. Okay. So in this case, electron is going from this neutral object to the positive charge particles, so then neutral out some of the charge particle over here, but then there will be more positive charge here on the other end over here, okay? After that, if you remove the rod, then this device will be positively charged, okay? So this is charged by contact. You can do also another way called charge by induction. So you are just having a charge rod that is approaching these two metal spheres. They are insulated with the ground, but they are in contact. Okay, so when you have this charge rod approaching these two balls, there will be charge distribution between the two balls. So according to opposite charges attract each other, so then you will have more positive charges on this end, which is closer to the positive charge. On the other sphere here, you will have positive charge here because like charge will repel each other, okay? So after that, you can make these two balls separated from each other. Then one ball will be negative charge, the other will be positive charge after you remove the rod. Okay, so in this case, the charge particle, the rod is not directly in contact with these two spheres, but you can actually charge the two spheres by just approaching this guy when they're in contact, and then after that, separate the two balls and then remove the charge rod. So then the two balls will be charged in that fashion, okay? If you just have one ball, but if you have a wire, you can ground the ball here. You can do the same thing for charge here, charge the ball here. But in this case, you are doing, again, charge by induction. You are not having the rod directly in contact with the sphere, okay? But approaching the sphere here first, so then charge will redistribute on this side and that side of the ball. Now ground the ball to the ground over here with the wire, so then positive charge will be moving to the ground because it will be repelled by this rod. After that, cut the grounding, so then this sphere will be negatively charged, okay? Even if you remove the rod. All right. So this is another example or another illustration of how the charged particles can pick up small pieces of neutral object. Okay, so now it doesn't matter if the charged particle is a positive charge one or it's a negative charge one. Okay, so fundamentally you will rearrange the charge distribution of the atoms in the material. So then opposite charge will be facing each other or are closer to each other than the same charges. Okay, so then in that case, you polarize the material so you can pick up small materials in that fashion. All right. The next section in the chapter talks about, so we say the like charges, they repel each other, opposite charges, they attract each other. So how much or how strong is the interaction here? So it's actually governed by Coulomb's law, okay? So the interaction between the charged particles, we use force because that's what the interaction is. So it's called electrostatic force. It's equal to a constant called K. All right, in this case, K is not the Boltzmann constant. Okay, it's the Coulomb's constant here. All right, but it's a constant K times the charges of the two charges you have. If you have two charges that are close to each other, so then it's Q1, Q2, you take the absolute values, divide by the separation of the two charges, okay? So that's assuming these two charges are small charges, so you can treat them as point charges. All right, so that's the magnitude of the force, interaction force between the two charges, where K is equal to 8.99 times 10 to the 9th newtons times meter square divided by Coulomb square, okay? Now the force is in the line that is connecting the two charges, okay? So if you have opposite charges, then you'll have attractive force, okay? If you have repulsive charge, or if you have the like charges, the same charges like positive to positive and negative to negative, then you'll have repulsive force. Okay. All right. In sign expression, people are writing it this in this way. So in some, you'll see that in some cases, people will write force equal to minus K Q1 Q2 over R square. This is for opposite charges. Okay. Then in some cases indicate by a negative sign. Okay. Or actually, in general, you can write this as F equal to K Q1 Q2 over R2 square. Okay. So then in that case, you'll see that if Q1 and Q2 are opposite charges, all right, then one will be positive, one will be negative. So then the force will be negative. Okay. So that means negative force for negative force. Okay. For the two opposite charges. You'll get positive force if two charges are like charges, because you'll either have Q1, Q2 are both positive or they are both negative. So then, sorry, you guys don't see this screen over here. All right. So in general, you can write in this equation, F equal to K Q1, Q2 over R squared. Okay. So if Q1 and Q2 are opposite charges, that means one will be positive or the other will be negative. So then the result will be having a negative force, right? Because positive times negative will be negative. On the other hand, if you have both are the same charges, either they are positive, positive or negative, negatives, they will give you a positive force. Okay, so the result will be force will be positive. Okay, so in that fashion, but just keeping that in mind. If you ever need to have those two scenarios, okay, in the same problem, then one force will be positive if they are like charges. The other case, if they are having opposite charge, then the force will be negative. Okay. All right, but this is the magnitude, and then direction could be determined by if what charges you have. Okay, it could be attractive force or the other way around, or repulsive force. All right. In astronomy, it's predicted that these two galaxies will collide in the future due to their gravitational attraction. Okay, so in large scale, when the distance of two objects are very far away from each other, so the gravitational force will dominate. Okay, in small scale, like inside atom, then electrostatic force will dominate. Okay, so this is what we have here. So if you look at inside an atom, so then this is what you have. So you can compare the two forces here, okay? So gravitational force or the Coulomb's force, all right? So you can see inside the atom, this is a hydrogen atom. The radius is about 5.29 times 10 to the negative 11, or about half, like 5.3 0.53 in Armstrong, okay, in that case. But you can calculate what's the gravitational force between a electron and a proton, okay? So it turns out to be in the order of 10 to the negative 47 newtons. However, for the Coulomb's force, the electrostatic force between these two, it turns out to be much larger, in the order of 10 to the negative 8. Okay, so that's like 39 orders of magnitude higher. Okay, so you can see in shorter distance, electrostatic or in very micro scope scale inside an atom, static force dominate there. Okay. Or we should say electric force is much larger than gravitational force, because Actually, in this scale, strong and weak interactions are stronger than the electrostatic force. But you don't have to know that if unless you are taking modern physics. Okay. All right. So let's take a look one example on Coulomb's law here. It says at what separation is the electrostatic force between a point charge of positive 13.1 microcoulombs. So mu c means microcoulombs, and the 26.1 microcoulombs point charge equal in magnitude to 1.779. Okay, so it tells you what's the force is equal to 1.77. The two charges are given. It's asking you to solve for the separation. So you can take a, so F equals to K Q1 times Q2, the absolute values over R squared. It tells you F is equal to 1.77 newtons. Q1 is 13.1 microcoulombs. Q2 is positive 26.1 microcoulombs. What's R? Okay. The constant K you're needed is K equal to 8.99 times 10 to the 9 newtons meter square over C square. Okay, so that's the constant you need. So you do want to convert your charges into the SI unit. Okay, it's given in microcoulombs. So that means you want to convert that into 10 to the negative 6 coulombs. So 13.1 times 10 to the negative 6 and 26.1 times 10 to the negative 6. All right, so let's take a look. So you're giving R a quantity, you're looking for R. Okay, so what you want to do is multiply both sides by R squared. to get rid of r squared on the right. Now divide both sides by f. Okay, so divided by f. So then r squared equal to that. So your r will be equal to square root of k, q1 absolute value and q2 absolute value over f. Okay, then you just plug in the numbers. 8.99 times 10 to the 9th Newton meter square over Coulomb square. Now Q1 is positive, so positive absolute value of positive will be 13.1 times 10 to the minus 6. Q2 is also positive, so 26.1 times 10 to the minus 6 coulombs. Okay. Divide by the 1.77 newtons. Okay. So sometimes you can check if your dimension is consistent. Okay, because you're looking for separation. So you'll see that this c square will cancel out this c and then this c. Okay, so that those two c's will become c square, cancel out that c square. The newtons and newtons will cancel out. So then under the square root, you have meter square. So your result should be in meters. That's correct. Okay, so your unit is right there. So then this will be 1.32 after you plug in your numbers in meters. Okay. All right. So one of you guys get like 1.32 e to the 6. So in that case, you probably didn't convert the charges into the SI unit, okay? From microcoulomb to coulombs. All right. Let me know if you have questions. All right. If you are clear, so then we'll take a look, closer look on the direction of the electrostatic force. Okay. So for force by nature, it's a vector quantity. So that means you want to know it's the magnitude, which is given by Coulomb's law, k q1 q2 over r squared. If you take the absolute values of the q's. Now for the direction wise, okay, so let's take a look on several different scenarios. If you have positive charges, then for one charge Q1, then it will be in this direction because they are in the repulsive force. So they are pointing away from each other. Okay, so then this guy will be in this direction, and this guy will be in the opposite direction. Okay, so those are the opposite directions for the direction wise, but the magnitude wise, they should be the same. They are governed by the Coulomb's law, Q1, Q2. Okay, so you can see the magnitude for these two forces are the same, the direction are opposite to each other's. For the scenario of if you have a positive charge and negative charge, now you will have attractive force. So that means they are pointing towards each other. Okay, so the two forces are pointing towards each other. However, they are still in the opposite direction, right? One is to the left, one to the right. The magnitude wise, they should be still the same because it's the k q1 q2 equation. All right. K q1 q2 over r squared. You take absolute values for the q's. So then the magnitude of the two forces should be still the same. The last case is if you have both negative charges. So then direction for the forces, they are again in the opposite directions. The magnitude wise, they should be the same again. Okay. So because you are taking k absolute q1 q2 over r squares. Okay. So in summary, if you have forces between two charges, whether they are like charges, positive or both negative, or they are opposite charge, one positive, one negative, then the forces on the two charges, they are having the same magnitude, but in opposite directions, okay? So it's actually a pair of action and reaction force for the two. They are action and reaction force, okay? According to Newton's third law. All right, now let's take a look on one example that involves the force, the action and reaction pair force here. Okay, so this is 2-point charges. The first one has charge of positive 3.13 times 10 to the negative 6 coulombs. And the second one is a charge of minus 4.47 times 10 to the minus 6 coulombs. They are separated by 25.5 centimeters. Find the magnitude of the electrostatic force experienced by the positive force. And then it's asking you what's the magnitude of the force experienced by the negative charge compared to the positive charge. Okay. All right, so I think this one is similar to the one before, but we can take a quick look here together. So you're looking for the magnitude of the force, okay? So you can just use the Coulomb's law here. Take Q1 absolute value, Q2 absolute value divided by R square, okay? One thing you do have to be careful about is the units here again. So this is 10 to the 9th. For the K, for the two charges, if you are taking just absolute values, so then positive numbers, 3.13 times 10 to the minus 6 coulombs, 4.47 times 10 to the minus 6 coulombs, okay? Divide by the R, the separation is given in centimeters, so you want to convert centimeter into meters, so 0.255 meters, okay? Here. It will give you about 1.93 as the magnitude of the force, okay? So the force is equal to that. Now part B is asking you what's the magnitude of the force experienced by the other charge, okay? So it should be the same because they are action and reaction pair. They should have the same magnitude, okay? So it'll be the same 1.93 newtons for this. But, right, yeah. So that means the same because they are action and reaction pair, okay? All right. So that's on that one. Let me know if you have any questions on this one. All right. So if not, then we'll move on. Now we can examine this scenario that is a little bit more complicated when you have more than two charges that are close to each other. Okay, so then if you are looking for the force on a particular charge, in this case, if you are looking for charge on Q1 here, then Q1 will experience a force from Q2, all right, in that direction, from Q3 in that direction, and from Q4 in that direction, all right. So the resultant would be the addition of those three forces together, okay. Now, this is again, because force is a vector, so then you will be doing vector addition, okay. So that means you can either do triangle method or like component method, okay. So you probably may want to do a quicker review on this if you don't know how to do this right away, all right. This is what you would be doing like graphically, okay. So graphically you are adding the vectors up one by one, okay. So that in that case, so it place the tail of the second vector on the head of the first one, and then place the tail of the third one on the head of the second one. So then the resultant will be from the tail of the first one pointing to the head of the last one, okay. All right. Let me see. So let me just make one more comment here before we look at this example, okay. So so if you have, so we learn Coulomb's law when the charges are point charges, okay. It also applies to spherically symmetric charge distribution. So that means if you have sphere that carries uniformly charged distributions and then interacting with another sphere of point particle, you can also apply Coulomb's law. Okay, so the K Q1 Q2 over R squared. In that case, R will be from the center of the sphere to the center of the other sphere or the point charge. Okay, but now let's take a quick look on this one here. It says if you have three charges Q1, Q2, Q3, they are the same magnitude of charge, but Q1 and Q3 are positive, Q2 is negative, okay? As shown in the figure. It's asking you rank the three charges in order of magnitude, increase in magnitude of the electric force they experience, okay? Indicate ties where appropriate. So let me stop sharing here and then show you how to do this guy here. All right, so you have three charges, positive, positive, and a negative. So now you have more than two charges, okay? So we'll just examine one by one. On Q1 here, you'll see that by Q3, this is 3, this is 1, this is 2, okay? By charge of 3, positive, positive charges, that means it's going to be in this direction, okay? Now, all these forces by any of these two should be at the same magnitude, because if you look at the interaction magnitude is K Q1 Q2 over R squared, because this is equilateral triangle. So the size, the separations are the same, okay? And then the charges, they are the same. So then magnitude will be the same, okay? So you should indicate the same length here. So this is F on 1 by 3. All right. Now F on 1 by 2 will be in this direction because they are opposite charges, okay? They are opposite charges, so then they are attractive force, okay? So the resultant of this two, if you use the graphically way, you can see that you move this guy to this way, so then the tail starts at the head of that one, so in this direction, okay? This will be your F1 to 2, all right? And just move this out. So then this will be the resultant, okay? This will be the resultant F1, okay? F1 here. So this is the same as this one, all right? This angle will be 60 degrees if this is an equilateral triangle, right? So this is 60, then this will be also 60 if this is equal to that. So this will be another equilateral triangle. So then this will be the same as the length here and here, okay? So just in the case. On this guy, you'll have attractive force by 1 on 2. So F2 by 1. And then on this one will be also the attractive force, okay? By 3 on 2. in that direction. You will then add these two up. Okay, so it goes like this way. You can move this one here over here. So F21, okay, and then resultant will be this guy. Okay, this would be F2, total force on 2. Okay, now you can see this one is larger than this guy, right? The total force on 1 is the same as this guy. So you can see that F2 magnitude wise should be greater than F1. Okay, you can see that already there, because this guy is longer than this. This is the same as that. Okay, we will take a look now on this here, F3, force on the 3. So there are two forces, attractive force, F3 by 2, and then repulsive force by 1. So F3 by 1 in that case. All right. Similarly, you are going to move 1. So the tail of it is at the head of the second one. So I'm moving this guy parallelly down here, F3, 2. And this is the resultant. Okay. F3. Okay, so you can see this is again a small equilateral triangle. So then this is the same magnitude for this total force is same magnitude as each of these two. Okay, so that's equal to F1. So F1 and F3 are the same magnitude. Okay, F2 will have the maximum or greater. So that's the order you could have. Okay, F2 is greater than F1, which is equal to F3. Okay. And then it's also, I believe it's also asking for the angles. Okay. So if this is the positive angle, like theta in that sense. So this is in the x direction. Okay. So the angle of F1 of 1, I can say theta 1 should be 0 degrees. Okay. This is B, sorry, C. This is part A. And then C is asking for the angle of F2. So in this case, you'll see that this is 60 degrees, but this is X direction, right? This is 120 degrees. 60 degrees divided into 2 halves. So then this would be 30 plus 120, okay? Theta 2 would be 30 plus 120, which is 150 degrees, okay? On that one. For 3, theta 3 should be measured from here. You can take this as angle theta 3, which is below the positive. Okay, so this should be 60 degree because this is 60. The whole thing is 120 divided by 2, so 60 here. Okay, you can say negative of 60 degrees. Okay, so that's the direction for charge 3 there. All right. Let me know if you guys have questions on this. If not, then we'll stop here. All right. So the lab will for Wednesday sections.